Your next assignment's due on Tuesday of next week. So as always, you have to upload that PDF before class starts on the day that it's due. Today we're going to be talking about manometers and a little more on the ideas associated with atmospheric pressure variation. Any questions in general before we move on to the new material? All right. A manometer is an improved way of measuring pressure. Do you remember what was the weakness with the piezometer as a pressure measuring technique? Right. If you put in a riser to measure the height of the water that's going to come out of that pipe, we're talking ridiculous heights of water required for a typical municipal network. So it's impractical for that reason, and also it's impractical for gases because gases would just escape out that piezometer tube. It's only usable for liquids. So a U-tube manometer is a way of overcoming those issues. What it is you've got a pipe and a tube connected to the pipe, but instead of having it go straight up out of the initial main pipe, you have a curve in it and an especially dense liquid. This manometer liquid has a greater density than what's usually flowing through the pipe. And if we use something, for instance, like mercury, which is really dense, then what it's going to mean is this delta H, the deflection that you're going to see, is much lower than the deflection would be if we were talking about water or oil, whatever it is that's actually flowing through the pipe. The other advantage of using a separate manometer liquid is that now you can have gases going through the pipe and measure the pressure. Because if you have a liquid as the manometer fluid, but then your fluid going through the pipe is like compressed air, then it's going to be fine. It'll be trapped and the air wouldn't flow through the manometer liquid. Conditions are static inside of the manometer, meaning this is in equilibrium. Water may be flowing through the main pipe. So here at 4, it's possible that water is flowing from the left towards the right. So there is bulk flow in this main pipe. But inside this little connecting tube, the hydrostatic equation applies because the water isn't flowing. It's static conditions. So if we wanted to use this to measure what is the pressure at the center of the pipe, then what we would do is we'd start where we know something. This U-tube manometer is open to the atmosphere, and we know the atmosphere as a starting point. We can say the atmosphere is 0 gauge. So where the air touches the water, the pressure of the water, or whatever this fluid is, in this case it's some manometer liquid, the pressure of fluid at 1 is 0. And then we go down, the pressure increases, and we could find out what is the pressure at 2 using the hydrostatic equation. So delta P is delta H times gamma, and that will tell us P2. How do you think P2 and P3 compares? Well, we're going down through the fluid to get from 2 to 3, so the pressure increases, but then the pressure decreases by an equal amount. So since 2 and 3 are at the same elevation, and since they're connected by one continuous fluid, so we're not changing from mercury to gasoline between 2 and 3, but it's the same fluid the whole way. Since it's the same fluid and since it's the same elevation, P2 and P3 are the same. Horizontal, no pressure change. But when we start going up from 3 to 4, the pressure decreases. And here we've got this length parameter L. So as we go from 3 to 4, we had P3, and now it's decreasing some delta P. So delta P would be delta L times whatever the unit weight is for that fluid. All right, so let's put that into practice. Let's try and calculate. If we're talking about mercury in that manometer, how can we find out the pressure at the center of the pipe? All right, so we start off with the pressure at 1. The pressure at 1, I'll just reproduce the sketch up on the screen, on the whiteboard. All right, so we've got our pipe, and we've got a U-tube manometer connected to it. And let me remind myself. All right. So there's some difference in elevation, the delta H. And what we want to find out is if the delta H is 0.45, so delta H is 0.45 meters, and if this L parameter from the interface up to the center of the pipe, if L is 1.83 meters, then what's the pressure at the center of the pipe? P4. And so I'm going to call this the location in the center of the pipe 4. And remember, 1 is at the interface of the air and the liquid. 2 was down here at this location. And here's 3. And 4 is at the center of the pipe. All right, so what we do is we say P1 is 0 because it's open to the atmosphere, and we're using atmospheric pressure air as our starting point. Okay, P2 is going to be P1 plus delta P. And the delta P I'm talking about, it's going to be P1 plus delta H times gamma of the manometer. Now we have to do a little bit of work up here to find the manometer gamma. So we're told that it's mercury, and the specific gravity is 13.6 for this mercury. So it's 13.6 times 9810 newtons per meter cubed. Okay, so that means that the mercury unit weight is 133,416 newtons per meter cubed. All right, so P2 is going to be 0 plus 0.45 meters of the mercury, 133,416 newtons per meter cubed. All right. Any questions so far? That tells us that the P2 is 60,037 pascals. And that's also P3. And we talked about how P2 and P3 have the same pressure because they're at the same horizontal elevation, and we connect them through a single fluid. P4, up there in the center of the pipe, is going to be P3 minus L times the gamma of water, because in this case it's water flowing through the pipe even though mercury was the manometer fluid. Okay, so P4 is going to be the P3 value of 60,037 pascals minus 1.83 meters of water. Now sometimes people talk about pressures as a depth of water. You know, you could say, you can use PSI as a pressure measurement. You can use pascals or millimeters of mercury. Well, inches of water or meters of water is another way of measuring pressure. So what I'm saying is the pressure at 4 is the pressure at 3 minus 1.83 meters of water. So all we have to do to convert that 1.83 meters of water times the unit weight of 9810 newtons per meter cubed. So that delta, the decrease in pressure, that is a decrease of 17,952.3 pascals. And so the overall P4 is going to be 42,085 pascals. So that's the pressure at the center of the pipe. All right, so any questions about that? Yes?
So when you, just to clarify, when you subtracted their P3 minus your change in height,
yeah,
times your gallon of water, and then you added it, so that's just due to your pressure is going to be lower at P4. You're going from a lower pressure to a higher pressure from the beginning.
Right, yeah, so exactly, yeah, we found the pressure at 3, you know, everything was additive to this point. As we went down, the pressures were increasing.
Right.
But then when we went from 3 to 4, that minus sign, we'd have to do a little bit of accounting. You know, anytime you're going down through the fluid, the pressure increases, but then when we're going up from 3 to 4, since that's upward through the fluid, that's why the subtraction there. The pressure decreases upward through the fluid. Are there other questions? Okay, so let's apply this to a more complicated system. Here we've got a series of 3 different fluids. We've got a pipe. Here at A it's a pipe, and so into the page is a pipe. But then there's a snaking series of manometers coming off of that. And what you have to do is try and find the pressure at A starting where you know something. In this case, we know something at the opening of the manometer. We know pressure is 0 at that interface. So before I turn you loose to collaborate with your classmates and find the pressure at A, just so that we're all on the same page, let's use the same numbering system for different interfaces. First of all, the water surface where the air and the water touch, let's call that 1. And then the interface between the water and the mercury, we'll call that location 2. Now, I didn't bother labeling location 3 at the bottom edge over here because we already determined that the pressure is the same on the left side and the right side as long as the elevations are the same and it's the continuous fluid. And so let's just call this interface 3. And the same kind of thing over here. We go straight to interface 4 at the junction of the oil and the water, and then you're going to have to go down to A. So we're starting P1 is 0. So what you should do is find P2, then find P3, then find P4, and finally find the pressure at A. And remember, the rule is as you go down through the fluid, the pressure increases. As you go up through the fluid, the pressure decreases. Be cautious about your dimensions. You're going to have to do a little bit of thought to find the right length parameter to use when you're applying the hydrostatic equation. All right, so I'm going to stop talking, pause the recording, give you some time to work through this, and then we'll go over the solution together on the screen in just a few minutes. Okay, so at the top here, I always do the preliminary stuff I'm going to need. If I know I'm going to later on use the specific weight of oil and the specific weight of mercury, I try and take care of that initially so I've got it ready to go. The pressure at 1 is 0, and then we go down to 2, so it's going to be plus some delta. So it's plus the change in pressure, which is going to be 0.9 meters of water. So that takes us to 8829 pascals. And then pressure at 3, we're going downward from 2 to 3 through mercury. So I'm going to use a different unit weight this time. The overall net distance vertically between 2 and 3 is 0.6 meters. So the pressure at 2 plus the difference. So the pressure at 3 then should be 88,878. And then now we're going from 3 to 4. The vertical parameter, like I said, it's the 1.5 meters that they tell us from the center of the pipe, but then the extra 30 centimeters, that's dimensioned from this edge down to 3. So that's why I'm using the distance of 1.8 meters, and we're going up through a fluid, so it's minus the delta P. And then finally, the pressure at A is going to be the pressure at 4 plus more change down through the fluid. So 89,500 approximately. So 89.5 kilopascals will be the pressure at A.
So you don't go to the bottom of the bowl?
Right. Yeah. The pressure at A is in the center of that pipe, right in the crosshairs. Other questions about this example? Manometers are just accounting. You're just applying the hydrostatic equation up and down. All right, let's look at differential manometers. A differential manometer is where instead of having one end open to the atmosphere, you've got that end that ordinarily would have been open to the atmosphere, you tie it back into the pipe again. And the point of doing that is that in a differential manometer, you're measuring a change in pressure rather than measuring the absolute pressure. You know, the pressure relative to atmosphere. We're using a change in pressure from one point in the pipe to the next. So here, what you can see is we've got this manometer connected at 1 and at 2. And if there's any deflection inside the manometer, it's going to be because of a change in pressure between 1 and 2. If this arrow wasn't there, indicating the fluid flow, would you be able to tell which direction the fluid was flowing from the manometer? Would that give you clues about the direction of flow? So if, let's say that it is this way, that the deflection is as shown in the manometer, but you didn't necessarily have the arrow. How would you know that the flow is going towards the right?
It's creating a head on the right-hand side of the pipe.
Okay, so what this manometer is showing is there's more pressure at 1 than there is at 2. And the evidence of that is it's pushing down enough inside the manometer. There's extra pressure on the left side of the manometer, and it's kind of deflecting that manometer fluid. And the reason why there would be more pressure at 1 than 2 is if water is flowing from the left towards the right, pipe friction is going to be taking away pressure. As the water goes along, pipe friction is extracting energy in the form of pressure. And so another way to think about it is the water wouldn't be flowing from left to right if the pressure wasn't lower on the right. You know, the water flows in the direction of where the pressure is lower. Just like the wind blows from high pressure towards low pressure systems. If you ever look at a weather map, the reason why there's wind is differences in pressure in the air. So the same thing is true in an enclosed environment like a pipe. So what this is showing is the water is flowing towards the right. This differential manometer is a way of quantifying the pressure difference between 2 points. Now this is a horizontal pipe. This is a very specialized case. Pipes aren't always horizontal. Sometimes they are, not always. If they are horizontal, then you can measure the change in pressure by the delta H and multiply that by the difference in the unit weights. So the difference between the manometer fluid and the fluid that's flowing through the pipe, and it is the rest of the fluid inside of these legs. So if we had mercury in there and water flowing through the pipe, we'd find the difference between the mercury unit weight and the water unit weight and multiply it by whatever the deflection is, and then that would tell us the pressure difference. It wouldn't tell us the pressure in the pipe relative to the surrounding atmosphere. It would just tell us how different is the pressure between 1 and 2. Because that's where the manometer is connected, is at 1 and at 2. More generally, the more useful form of the equation that we can have is this change in piezometric pressure between 1 and 2. This applies even if the pipe isn't horizontal. And by P sub z, what we mean is, you've seen this before, it's pressure plus gamma z. That's the definition of piezometric pressure. In piezometric pressure, at a single location, you're keeping track of not only what is the pressure at that location, but also how high is it above a certain datum, some z point that you're measuring all of the other elevations relative to. So here in this pipe, what we've got is we're saying P sub z1 minus P sub z2 is equal to delta H times gamma mercury minus gamma of whatever the other fluid is. So it's like saying P1 plus gamma z1 minus P2 minus gamma z2 is equal to delta H gamma mercury minus gamma of the other fluid. If it's horizontal, z2 and z1 are equal. So if it's horizontal, those two terms cancel out, and then all it turns out to be is delta P, P1 minus P2. So that's why we have this simple equation up top in terms of delta P. If it's horizontal, z1 and z2 are the same. Now, piezometric pressure, it's still a pretty new idea, so let's get some experience solving a problem having to do with piezometric pressure. That's what this next example is. This next example is we have an inclined pipe, and we're using a differential manometer to find out what is the pressure at 2, and then what is the change in piezometric pressure between these two locations. All right, let's go through the steps of finding P2 and also the change in piezometric pressure. Remember, the chapter we're in right now is using the hydrostatic equation. So to find the pressure at 2, there's basically two routes to get from 1 to 2. You'll notice water is flowing through this pipe. And so if we want to find out the pressure at 2, you can see here at 1 we know the pressure. The pressure is 450 kilopascals. Well, to apply the hydrostatic equation, we can only apply it in environments where the fluid isn't flowing. And it is flowing through the pipe. So we can't apply the hydrostatic equation there. It doesn't apply. But it does apply down this scenic route. This scenic route, the conditions are static. We've reached some equilibrium with a deflection in the manometer. So it's a perfect place for us to use the hydrostatic equation. So for find P2, the approach that I'm going to start with, I'm going to say the pressure at 2, P2 is equal to, all right, starting with P1, P1 plus delta Y gamma of water plus delta H times gamma of water minus delta H times gamma of mercury minus delta Y times gamma of water minus delta Z times the gamma of water. So basically, what we did was we said, start with the pressure at 1 and do the up, down, add, subtract thing that we've already been trying today. And eventually, you're going to get to location 2. So starting here at 1, we know the pressure is 450 kilopascals. We're going down delta Y through water. So that's why I did plus delta Y times gamma of water. Okay, so now we're here. We'll find the pressure there. And then we go down a little bit further. So down delta H times gamma of water. And we jump over to this side, and we're going up, so it's a minus. So minus delta H times gamma of the mercury. And now we go up delta Y through the water, so minus delta Y times water. And then we're going up. This last distance is Z2 minus Z1. I've called that delta z. So some incremental distance delta z, and it was minus because we were going up. And then where are we now? We've made it all the way back up here to location 2, so that's why it's equals P2. Okay, so we're just applying the hydrostatic equation through the manometer tube, one dimension at a time. We have some of these dimensions. Others of them are going to just cancel out. For instance, we have minus gamma y times water. Over here we had plus delta y times gamma of water. So we can cancel that out, right? Yeah. So what's left is going to be P1 plus delta H times gamma of water minus delta H times gamma of mercury minus delta Z times gamma of water is equal to P2. So let me show you those substitutions, putting the numbers into the formula. So here's the formula I've just been talking through so far. And we actually substitute in the known value for P1, 450 kilopascals, plus the delta H increment of 5 centimeters converted to meters, 0.5 meters, times the water. So it goes up a little bit as we move down through the water. And then you decrease some pressure as you move upward through the mercury. And then minus that final delta Z distance of 1 meter through the water. So the pressure at 2 is going to be lower than the pressure was at 1. And there's two reasons for that. We have an inclined pipe. Water's flowing from location 1 towards location 2 in this example. So the pressure at 2 is partly going to be lower because of pipe friction, but it's also, the pressure is lower at 2 because of the difference in elevation. So there's two reasons why the pressure is going to be lower at 2. And this process that we went through of using the manometer to connect these 2 points of interest will take both of those factors into account. And as long as we know the pressure at 1, the differential manometer can tell us the pressure at 2. All right, so this may not make sense the first time you have to see and work through a problem like this, but you just stick to what you know, and the hydrostatic equation is what you know. You know, as you go down through fluids that are static, the pressure increases. If you go up through fluids that are static, the pressure decreases. And you can just apply that through the scenic route of the differential manometer and eventually get back up to point 2. All right, the second part of the example is asking, what is the change in piezometric pressure? Okay, so the delta PZ. So delta PZ, delta P sub Z, our formula for that is delta H times mercury, gamma of mercury minus the gamma of whatever the other fluid is. In our case, it's water. All right, so the delta P sub Z, we've got 5 centimeters is the deflection inside the differential manometer, and the difference between the unit weight of mercury and the unit weight of water means that the change in piezometric pressure is 6159.5 pascals. So how does that compare to the overall change in pressure that we saw in the first part of the problem? You know, when we did this first part of the problem, P2 was 434,030.5 pascals. And so the delta P was 450,000 pascals minus 434,030 pascals. Anybody with a calculator tell me what's that difference? 450 minus the pressure at 2. So that what was the delta P? 434,030.
15,970.
Thank you. Okay, so the total pressure change between 1 and 2 was 15,970 pascals. Remember, the two reasons for the pressure change is because of pipe friction and because of elevation differences. What this change in piezometric pressure that's shown here on screen, the 6159.5, that is due to pipe friction. That's what the differential manometer is measuring, is the pressure change due to pipe friction. So it kind of already takes into account any pressure difference that might have arisen due to an elevation change between the two. And that's what's nice about a differential manometer is if conditions were static, meaning if there was no fluid flowing through this system, so if we turn off the velocity and there's still liquid in there but it's not moving anymore, this delta H deflection would go down to 0. This deflection only exists because of the fluid is flowing from 1 towards 2 and there's pressure loss because of the pipe friction. That's what this differential manometer is measuring.
So are these manometers, are they something that are installed in the field or installed in certain places or what?
Great question. Yeah, that's a good question. We're still talking about something that probably isn't used in a modern day water distribution network, but it would potentially be used in a research environment. If you wanted to measure differences in pressure, like in a lab, you'd maybe see a differential manometer like this. Maybe like at a water treatment plant, the kind of place where there would be easy visual access, but not like the water pipes that are under the road. Okay, so piezometric pressure. It'll be something that we'll return back to a couple of times through the semester, so it's important for you to kind of memorize not only that P sub z equals P plus gamma z. You need to memorize that, but also like what it means. If we have a tank of water and there's two locations that we're interested in that tank, the piezometric pressure is the same between 1 and 2. Even though the pressure at 2 is higher, the piezometric pressure is the same because if you go down through the fluid, you're losing Z, but you're gaining P. And so piezometric pressure is conserved in a static environment. It's when the fluid is flowing that there will be a difference in piezometric pressure. Another way of expressing this piezometric idea is instead of expressing it as a pressure, sometimes you'll hear people talking about piezometric head. And piezometric head is where you just divide the pressure term by gamma, and then you also divide this gamma z term by gamma, and so the two gammas cancel out and you're just left with the z. And so head is sometimes, they describe the height to which water will rise as head. So in a piezometer, if you've got that pipe and you puncture a hole in the pipe and water's spraying all over the place, well, remember in a piezometer what we do is we puncture the pipe and then we put a confining tube. So the water level is going to rise to a certain height, and they call that how much it's sticking out of the pipe, they call that the head. So it's a reflection of pressure. So you can either talk about, well, what's the pressure at this location, or you can say, what's the head at that location? And so head is just a way of expressing a pressure in terms of length by dividing by the unit weight of whatever that fluid is. So a change in piezometric pressure, the head version of that, the change in piezometric head, you can see the formula for that. All right. Here's a picture of a weather balloon. I've never seen a weather balloon in person, but I've seen like videos of them. floating off into the sky. And they do that. They use weather balloons to find out what is the temperature at different elevations. Because understanding the temperature profile as you go up through the atmosphere can tell you important things about, for instance, how pollution is going to spread out. It turns out that if you have a smokestack, the smoke can either go up or the smoke can go down. And there can be something called fumigation of the downwind area, where the smoke is trapped because the atmospheric conditions above are what's called an inversion. So for a variety of reasons, they send these weather balloons up into the sky to measure the temperature profile. But what I'm asking specifically with this picture is, you can see here's the balloon and it continues. There's a lot more slack in that balloon. They haven't filled it all the way. Any guess why not?
If it heated up, it would and if it was completely full, it would pop.
Okay, if it was full, it could pop. Yeah, if you've everybody when they were a kid let go of their balloon, right? As the balloon goes up in the atmosphere, eventually it pops. Why do balloons pop?
To reduce the pressure.
Okay, so the pressure surrounding the balloon is going to decrease. You know, up in the atmosphere, the pressure is very low. That's why if the window falls out of the airplane, everyone's gasping for air. There's not enough pressure to force the oxygen into your lungs. So those little masks drop down, and those aren't pressurized, but it's feeding you a higher concentration of oxygen. And so the low pressure that you're breathing is enriched with oxygen, so the net difference is you'll still be able to live, because the partial pressure of oxygen would be the same since the concentration is higher. But back to this example, at sea level, there's lots of pressure surrounding the balloon. So it's keeping this volume of gas. They've put a certain amount of helium in this balloon. The surrounding pressure is keeping it in a pretty small volume. But as the balloon rises and the atmosphere surrounding the balloon gets less and less pressure, then that same volume is going to occupy more space. And so they have to give it room for those helium molecules to spread out, since the surrounding pressure won't be confining it as much. Here is a graph that shows the temperature change of the atmosphere, and it's because of the decreased density as you go up through the atmosphere that there's a consistent decrease of temperature. The two go hand in hand, and it's a pretty linear relationship as you move up through the troposphere, that for every kilometer of elevation you lose 5.87 degrees Kelvin. That's called the lapse rate, the decrease in pressure with elevation. So that alpha parameter is the lapse rate of typically 5.87 Kelvin per kilometer. And that can change a little bit depending on the humidity. How dry the air is has an effect of how much the temperature changes as you go up through the atmosphere. Here's a formula that defines the pressure variation in the troposphere. Inside the brackets, it is the temperature aloft. So this T is the temperature at some elevation. So T is the temperature at elevation of Z, where T naught is the temperature at a known location of elevation Z naught. So it might be ground level or sea level. You know, wherever you know the elevation and temperature is the starting point, and we want to find the temperature some distance up in the air. So what this formula is able to predict is, it says if you know the temperature aloft, so we're kind of inserting that other equation into this one, and you know the original temperature, then for a certain gas constant, we can use the gas constant for air as the R value here. This relationship will predict what's the pressure at a certain elevation, depending on if you know the pressure at your original ground level and the temperature at that elevation, and then how the temperature has changed at the elevation of interest. Okay, so just to illustrate, let's use the pressure variation in the Burj Khalifa as an example. And I've been to the top of the Burj Khalifa, and it's noticeably cooler up there. On a hot day, it's slightly less hot up in the observation deck. It's still pretty hot, but it's breezy at least, and the temperature is reduced. If you'll bear with me, we've got, it's 12:15 right now, but if we take 2 minutes just to look at this example, I think it'll make your homework quite a bit easier. So let's say that we know the elevation at ground level. It's 10 meters above the sea here at the base of the Burj Khalifa. So it's 30 degrees Celsius there, and our starting pressure is 97189 pascals at the base of the Burj Khalifa. Let's find out what's the air temperature at the top and the air pressure at the top. So let me just show you how to do this. First of all, we need to know our lapse rate, alpha. So we have it in terms of Kelvin per meter. And also, this is the R value for air. So that's the gas law constant for air, 287 joules per kilogram Kelvin. All right, so let's substitute that into the formulas and find out, first of all, what's the temperature decrease. So we can solve this in terms of Kelvin. So if the temperature was 30 at the base of the Burj Khalifa, that means it's going to be only about 25.14 Celsius at the top. So 5 Celsius is quite a bit cooler. That's a big decrease in temperature. But more importantly, if we take that temperature, then we can substitute it into this formula to find the pressure at the top. And so this exponent factor here, G divided by alpha times R, I found that component here. So 9.81 for G. Alpha is the lapse rate in terms of Kelvin per meter. And the R value is the constant. So the pressure is going to be a little bit lower when you go 800 meters into the sky. So this was our initial pressure. It's the ratio of the temperatures to the exponent. And you can find the pressure aloft. So hopefully that illustration, remember that the example, if you didn't have time to copy everything down in a rush, that example is posted on YouTube. But I can leave it up on the screen for a few minutes if you do want to write down the numbers. Just remember, let's take one last look at the announcements here. The assignment's due on Tuesday. I'm going to try and have these quizzes graded today or tomorrow, and I'll put the scores in MU Online. I've stolen 3 minutes of your life. We went over by 3 minutes, so I'll pay you back with interest next week. All right? Have a good one.